This is my lab 6, where we'll be dealing with magnetic molasses. The purpose of this lab is to investigate Faraday's law by observing what happens when a bar magnet falls through a conductive aluminum foil tube. The magnet produces a magnetic field that induces an electric field and current in the tube. The induced current produces its own magnetic field, which affects the speed at which the magnetic bar falls. The results of my experiment show that the bar takes 1.25 seconds to fall in real life, and in the computational model of my experiment, the bar took 1.374 seconds to fall. Here are the fundamental principles and formulas you need to know for this lab. The Biot-Savart law describes the magnetic field generated by a constant electric current. Faraday's law says that a changing magnetic field creates an electric field. And Newton's second and third law states that force equals to mass times acceleration, and that every action has an opposite and equal reaction. In my experiment, the system is the bar magnet and the surrounding is the aluminum tube and everything else. The procedure for this experiment is to drop a bar magnet into the aluminum tube and then record the time it takes for it to fall through. And here are the results from the experiment and the data used for my calculations in the computational model. The magnet's mass was 0.025 kilograms, and the mu was 1.5 am squared, which we found in lab 4. The tube's length was 0.3 meters, and the tube's width was 0.01 meters. The tube's inner radius was 0.015 meters, and the average time it took for the magnetic bar to fall through the tube was 1.25 seconds. And now here's the initial conditions for my code. The first part generates a computational model of my tube, and then the second part generates a computational model of my magnet. Here's the second part of my code where I created a function to calculate for the magnetic field of the dipole, which is the bar magnet, and then another to calculate the magnetic flux of the falling magnet. Here's the last part of my code, which updates the velocity and position of the bar magnet by finding the magnetic force on the bar magnet as well as the gravitational force on the bar magnet and updating the velocity and position using Newton's second law. And here's the final result of my code. And as you can see, the final time that I took for the magnetic bar to fall through the tube was 1.374 seconds, which is really close to our actual in real life time. And the possible errors could be caused by air resistance and other unknown outside forces. Here's our assumptions we made for this lab, as well as some possible errors that we could have made. The bar magnet was treated as a magnetic dipole so that we could use the magnetic field equation for a dipole in the computational model. We also treat it as if there was a negligible air resistance, as well as the fact that there are no other outside forces affecting the bar magnet in our equation. For some possible errors that we could have made, the electronic and magnetic devices could have affected the data of our bar magnet, as well as the fact that there could have been friction caused by the tube as the bar magnet went through the tube. There could have also been some human errors in calculating the data and the time. Now we're going to answer some questions related to this lab. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The induced current in the aluminum tube would become greater, as the current is equal to voltage divided by R. And if R is reduced as close as possible to zero, then current would be increased infinitely close to infinity, which would create a greater magnetic force on the bar magnet, resulting in a slower time for the magnet to fall. What if holes or slots were cut into the tube? How would this affect the ring current in your model? The induced current would be less due to the holes impeding the current in the tube, which will result in the magnetic bar falling faster.